Hey class, so this is just going to be a short video talking about the crossflow heat exchanger that we tried to work on in class on Wednesday. I had some trouble setting this up in a way that SolidWorks was able to solve and kind of give it results that made sense to me as I was going through it. So before I talk about the simulation, let me just go through the model itself so you can see how this thing is composed. And what we have is we have a series of plates. So there's the back plate, which itself is just a plain aluminum plate with rounded corners. This one is actually 8x3. I made it a little bit longer to improve the performance a little bit so we could get a little bit more mass flow through there. And then there are some gaskets between the back plate and the various center plates. So I'm going to open that up so you can take a look at that. In class, we had modeled the gasket as being part of the extrusion of the plate. Most of the heat exchangers that I've found, the plates actually use a gasket to control which ports on the plates have the ability to flow through them or not. So in the assembly, we actually have two gaskets, one kind of going from top left to bottom right, and then we just flip it over and use it on the other side to go from the top right to the bottom left. And that works out pretty well in terms of reducing the complexity of parts, as well as, kind of getting the crossflow that we want. The center plate looks a lot like the back plate, except for it has holes to allow flow through it. And the top plate is actually, I just used the center plate again in this model. So you can see we have a stack up where we have the back plate. And then after the back plate, we have a gasket. I guess it's not in order on here, but here's the gasket. And then we have a center plate and then another gasket. And then it's hidden, but I have another center plate on top to be able to close off the flow on there. And then I've just hidden that center plate so we can see the flow inside the part as we're going through it. Another thing that's kind of worth noting is that these lids are created off the center plate. And one of the issues I had is that as I change the thickness of this part, these lids are not actually attached to the plates themselves. And as you can see that they're underdefined in this case. So one of the things that you might want to do if you're doing a lot of revisions to this is go back into the assembly and mate these lids in place so that way they can move with changes to the part. Or maybe just manually create them as separate parts or as part of an existing component rather than using the lids tool, because I found that it was somewhat cumbersome to go through. In the simulation, so I'm going to go back over to the flow tab. Again, I use the wizard to build out the simulation. The settings on this case are just inch, pound, second. I'm doing an internal flow with heat conduction in the solids. I'm just using water in this case, but we can use two fluids if we want to. I was just trying to decrease the computational complexity. And then I also used aluminum 6061 alloy as the solid material inside this project. I have two fluid subdomains in the system. So I'm going to show you what those look like. That's the first one. It's the hot water inlet side. And then I also have the cold water inlet side. So I didn't want to necessarily edit it. I just wanted to show it. So I'm just going to show that. And that one, you can see these two domains don't actually touch. They're separated by the center plate. So they are totally independent. And that's the thing you got to watch out for. I did find that if I wanted to specify environmental pressures, I need to make sure that I have those set up as separate conditions on each of the fluid domains. So I can't have one environmental pressure condition that crosses multiple fluid domains. That gave me an error, which is something we should watch out for. Let me hide those again. I went down to just using essentially one separator plate between a top and a bottom section because these thin fluid domains took a long time to solve computationally. And so I actually had to go through and make the plates a little bit thicker and decrease the number of them to make it solve in a reasonable amount of time. But we can see that these are working the way that we expect them or want them to. So if I look at I'm going to hide these trajectories for a second. So I'm going to hide these flow trajectories. We can see that On the inlet side, the hot water flows down, and then as it flows down, it's cooling off, and then the cold water is actually flowing up. Then it's heating up as it goes across. And if I were to extend this plate out, then the outlet from the cold water side would be closer to the inlet temperature on the hot water side, and vice versa on the cold side. If we show those trajectories again, and actually I can animate these, so I'll play those out. We can see the water flowing. And again, the hot water is flowing in on this port, coming across the top of the plate, and then flowing out the top on this side. The cold water is coming in on the bottom, again, kind of flowing up through the plate and heating up, and then flowing out on the opposite side. So I have an inlet here and an inlet here. They're crossing and they're leaving, the hot water leaves at a colder temperature and the cold water leaves at a higher temperature. Right now, the hot water is actually leaving at a temperature that seems like it's still a little bit above the outlet temperature of the cold water. But if I were to extend this plate and make it longer, or decrease the flow, or add an additional plates, that I could get a larger heat transfer going through. Another thing that's important to note from looking at this, let me hide those flows one more time, is that I found in this analysis that the thickness of the center plate was not as important as the thickness of the fluid domains. So in this case, you notice there's not very much heat differential between the center plate, which I have highlighted here. I actually can't really see it very well, but it's this plate here. Notice the temperature differential through the thickness of the plate is almost constant. So the thickness there was not that important, but I do have a pretty significant temperature differential in the fluid domain between the center plate and the top plate, and the center plate and the bottom plate. And therefore, having a thinner domain for the fluid is more important than having a thinner domain for the plate. Obviously, there's no advantage of having a thicker plate other than it being more rigid. But that's one of the things that's important for kind of analyzing the design of a system like this. So hopefully that makes some sense and is a helpful example for you to take a look at. And if you have any questions, please feel free to let me know. Thank you. Bye.